Okay, I'm going to try and go over the PCM transmitter, the block diagram. So what happens if you have an analog signal coming in? So a signal that might do that. Why do you need a low pass filter? Well, a low pass filter will block any frequencies above the ones you want. So for example, for hi-fi, we can hear up to 20 kilohertz. That's our frequency range. So you don't want 22, 23, 24 kilohertz going through there. And that would happen, if it's audio, all music has harmonics of notes. So you don't want anything above that going through. If you do, you get something called aliasing. And basically that's related to the Nyquist theorem. You basically need to sample at least twice the highest audio so you can get a decent representation of the signal. If you don't do that, you get aliasing. Okay, so the low pass filter filters out any unwanted frequencies above, in this case, 20 kilohertz. Okay, just check the question. It might not necessarily be 20 kilohertz. It might be 10 kilohertz. It depends. Sample and hold. Well, basically, if you've got your audio signal doing that, you need to take samples of the signal. So at every predetermined amount of time, you'll be taking samples. The more samples you take, the better the representation of the audio signal. But the downside is the more data you have to send. Okay, so there's a trade-off. So you've got the sample, and obviously a sample clock there, which is taking samples. Then it goes into your ADC, analog to digital converter. This is what an ADC looks like again. You did this in component 1. Hopefully it won't come up in component 2. This is a 3-bit ADC. So hopefully you can see, start down here. That's with no voltage going in. As I increase the signal voltage, that number 1 comes on, then number 2, and then obviously number 3, then 4, then 5, then 6, and then 7. Yeah. So the idea is you've now got an analog signal going in, like that, and you've literally got bits coming out. You've got ones and zeros coming out. So you've converted it into a digital signal from the analog. So this will be a 3-bit DAC. Okay, so that's what that one does. It's a flash converter, the one with all the resistors and the all the op amps. Then this is a bit that some of you might be confused with: the parallel in, serial out shift register. It's very easy. It's just a shift register, but obviously it will take 1 clock pulse for, let's say it's a 3-bit one, for those 3 bits to get in. Then it will clock those out in a serial fashion. Because obviously the information wants to go that way as a bit stream. Yeah, all these ones and zeros will go off. It could be down the internet. It could be via a USB. That's called a serial bus. Those sorts of things. So, what does a piezo shift register look like? Let me go back onto this. Okay. So this one here is a normal shift register. Okay, and by normal shift register, I mean that the Q from one goes into the D of the next, and you've got a common clock pulse. Okay, the only difference is you've got the idea of being able to put bits in. So this is a 4-bit shift register. So if I was to put, I'm just going to clock these. I've already got ones defaulted. I'm going to clock those through. So ignore that. Okay, so let's put, for example, a 1 there and a 1 there in. It will take 1 clock pulse to load it in. So that information now is loaded. Yeah? So that was from the ADC. It was a 4-bit ADC. That data would come in like that. Okay? So that's loaded in now. Then it will take the next clock pulses to get the data out. So my data is 0, 1, 0, 1. So the output there, I've got a 0, then I've got a 1, then I've got a 0, then I've got a 1. So that's my data out. The 0, 1, 0, 1's come out. Yeah, I'm left now with my next bit of data that can come in. So let's say I've got a really, really, really high note, and I'm representing the number 15 for the highest note possible. Yeah, or It should actually be loud note, shouldn't it? But anyway, so that will take 1 clock pulse to go in, and then the next 4 to go out. So you got 1, 1, 1, 1. Okay. So that is basically what the parallel in serial out shift register does. Okay. So some of you might be confused because you have to do it as a timing diagram sometimes. So as an easy sort of view of that, if my data is at QA, then the information would shift through to QB and then shift to QC and then shift to QD. That's what would happen. The only difference is because it's a parallel in serial out, you might get data at QA, B, C, and D in the first clock pulse. Then it gets a bit awkward because that data would still need to shift through from A to B, from B to C, and from C to D on the next few clock pulses. What I would really suggest is actually have a look at a component 2 paper and see if you can look at those questions and sort of understand the timing diagram related to this. Obviously, come for boost sessions as well. But going back to this one, then there we go. So things you might get asked. You might get asked. Why would you use a low pass filter? Because you want to remove any frequencies above the break point, and it stops something called an effect called aliasing. Yeah, because you need it to be twice the highest audio. So they could ask you about that. They could give you the frequency there. Another thing they could ask you is looking at the sample clock. They could give you something where you've got some data like that, and then they could give you like this is where the samples are, those 3 points. Could you plot the output down here? And all you would do is you'd just literally do the shape of that, and it would look like that, whatever it would at those sample points. They could say, what would be the frequency here if the frequency here, let's say, for example, is 40k, and and if it's a 3-bit DAC, if it's 3-bit, then this would have to be 3 times faster. It will be 120 kilohertz because the information needs to shift out before the next sample comes in. They might even give you a bit of time division multiplexing. They might say that the data takes this long from the sample clock, and then the next sample comes in then. Then they might say, how many other channels can I get down this PCM link before that next bit comes in? And it'll just be a simple, we'll count how many would fit in there before the next sample comes in. Yeah, so that's kind of what the sorts of things they ask. They can bring in a TDM bit on that one as well. But hopefully that's helped a little bit. I'll explain the PCM receiver on my next video, and that will obviously have the Schmidt trigger. There's always marks on the Schmidt trigger, inverting, non-inverting as well. Again, they're not too difficult. It's literally Ohm's law and circuit rules. As you know, I bang on about that every single lesson. That's all it is. It's Ohm's law and circuit rules. I hope that this has helped.